Hello students, today under the subject area of food engineering, we will be discussing the introductory module. Food engineering is a significant component of the typical curriculum for undergraduate degree in food science or food technology. Food engineering is integral and significant component to understand theoretical aspects of food processing into practical implications. Physics, chemistry and mathematics are essential in gaining an understanding of the principles that govern most of the unit operations which are commonly found in food industry. Foods undergo changes as a result of processing. Such changes may be physical, chemical, enzymatic or microbiological. As a food engineering student, it is essential to understand the quantitative analysis of unit operations, and therefore your ability to use or apply mathematics is essential. The basic concept of units and its implications is highly significant for learning various aspects of food engineering. This module is divided into following subsections: contents, concept of unit operation, SI units, unit conversions, dimensional analysis, conservation of mass, conservation of energy. The first unit, concept of unit operations. In all the processing industries such as food, biological or chemical, there exist similarities where feed is processed into final products. These processing steps could be chemical, physical, biological or in combination, and are usually separate and distinct steps called unit operations. Classification of unit operations. Unit operations can be classified as follows: fluid flow deals with principles that determines flow or transportation of fluid. Heat transfer deals with principles that govern accumulation and transfer of heat and energy. Evaporation, a special case of heat transfer which deals with evaporation of constituent from a solution. Drying, operation where volatile liquids, usually water, are removed from solid materials. Distillation, operation where components of a liquid mixture are separated by boiling based on vapor pressure difference. Absorption, process in which a component is removed from a gas stream by liquid treatment. Membrane separation, process involving separation of a solute from a fluid by diffusion of this solute from a liquid or gas through semi-permeable membrane barrier to another fluid. Liquid-liquid extraction, process where a solute in a liquid solution is removed by contacting with another liquid solvent which is relatively immiscible with the solution. Adsorption, process where a component of a gas or a liquid stream is removed and adsorbed by a solid adsorbent. Liquid solid leaching, a process where a finely divided solid is treated with liquid that dissolves out and removes a solute contained in the solid. Crystallization, removal of a solute such as salt from a solution by precipitating the solute from the solution. Mechanical physical separations, this involves separation of solids, liquids or gases by mechanical means such as filtration, settling, size reduction, which are often classified as separate unit operations. Unit 2, SI system of basic units. To analyze and quantify physical processes or unit operations, understanding units and dimensions of the physical quantities becomes essential. There are three main basic unit systems employed in engineering and science. The SI system, which stands for International System of Units. The three basic units under SI system are the meter, the kilogram and the second. 2. FPS system. Three basic units of FPS system are foot, pound and second. Third, CGS system. The three basic units of the CGS system are centimeter, gram and second. Presently, SI system has been adopted officially for exclusive use in engineering and science. Derived units of SI system. These units have special names which are usually algebraic combinations of base units expressed by means of multiplication and division. For simplicity, derived units often carry special names and symbols that may be used to obtain other derived units. Common units and conversion factors. Unit conversion is a multi-step process that involves multiplication or division by a numerical factor. For instance, 12 feet 5 inches is converted to inches as follows. 1 foot is equivalent to 12 inches, therefore, 12 feet would be 12 multiplied by 12 inches, which is equal to 144 inches. Hence, 12 feet 5 inches is equal to 144 plus 5 inches, which is equal to 149 inches. Unit 4, dimensional analysis. Dimensional analysis is a tool to represent the relevant data and how to depict the same. It is a useful technique for experiment-based engineering fields. It is a means of simplifying a physical problem by appealing to dimensional homogeneity to reduce the number of relevant variables. Dimensional analysis is particularly used for presenting and interpreting experimental data, attacking problems not amenable to a direct theoretical solution, checking equations, establishing the relative importance of particular physical phenomena, and finally, it helps in understanding physical modeling. In dimensional analysis, we are only concerned with the nature of the dimension, that is, its quality but not its quantity. The following common abbreviations are used. For length, the dimension is capital L. For mass, it is capital M. For time, it is capital T. And finally, temperature is represented as theta. We can represent all the physical properties we are interested in with L, M and T. Sometimes theta could be included. Dimensional homogeneity. Any equation describing a physical situation will only be true if both sides have the same dimensions. That is, it should be dimensionally homogeneous. For example, we take Bernoulli's equation where P plus 1 by 2 into rho into V square plus rho GH is equal to constant. Here the P stands for pressure, the rho stands for density, V for velocity, H is the elevation and G is the gravitational acceleration. The SI units for each term on the left hand side should be consistent and equal. For instance, the unit or the dimension for P is equal to m into L power minus 1 into T power minus 2. Hence, the dimensions for P should match with the dimensions for rho V square, in turn should match with rho GH. So, we would like to deduce the dimension for the term rho V square. Rho V square is equal to the dimension of density, that is m into L power minus 3 into V square, that is the dimension square for the velocity, that is L into T power minus 1 whole square. When we multiply these two dimensions, we end up with the net dimension m into L power minus 1 into T power minus 2. Similarly, for rho GH, here the term rho GH involves multiplication of density into gravitational acceleration into height. Hence, the net dimension for rho GH is m into L power minus 3 into L into T power minus 2 into L, which is again matching with the dimensions of terms P and rho v square, which is equivalent to m into L power minus 1 into T power minus 2. The units of the right hand side must be the same, hence the constant will always have dimensions of m into L power minus 1 into T power minus 2. That is, the units are consistent. Dimensional homogeneity is a useful tool for checking formulae. For this reason, it is useful when analyzing a physical problem to retain algebraic symbols for as long as possible, only substituting numbers right at the end. However, dimensional analysis cannot determine numerical factors. Example, it cannot distinguish between 1 by at square and at square. This property of dimensional homogeneity can be useful for checking units of equations, converting between two sets of units, defining dimensional relationships. Let us move to the unit 5 of this module, conservation of mass. The principle of conservation of mass states that mass can be neither created nor destroyed. However, its composition can be altered from one form to another. The conservation of mass principle is given by the following equation: rate of mass entering through the boundary of a system minus rate of mass exiting through the boundary of a system is equal to the rate of mass accumulated within the system. Let us see the figure. If the rate of mass accumulation within a system is 0, then the rate of mass entering must equal to the rate of mass leaving the system. For example, as shown in the figure 1.1, the level of milk in a tank remains constant. The milk flow rate at the inlet is 1 kg per second, then the flow rate of the milk at the exit must also be 1 kg per second. Next, let us convert the previous equation into a mathematical form. To do this, we will refer to figure 1.2. The figure 1.2 shows a system with mass inlet and exit streams. Although only one inlet and one exit stream is shown, there may be more than one stream entering and exiting a control volume. Therefore, for general case, the rate of mass flow entering the system is denoted by m dot subscript inlet, which is equal to sum of n streams which are entering the system. Here, the summation is given by sigma I equal to 1 to n m dot I, where subscript I denotes the inlet and n is the number of inlets to a system. The rate of mass flow entering the system is m dot inlet is equal to sigma I equal to 1 up to n m dot subscript I. Similarly, the rate of mass flow exiting the system would be m dot exit, which is equal to sigma E equal to 1 to P m dot E, where the subscript E denotes the exit, P is the number of exits from the system. The rate of mass of accumulation within the system boundary can be expressed as a function of time. M dot accumulation is equal to dm system by dt. Then substituting the above equations into the main equation, sigma I equal to 1 to n m dot I minus sigma E equal to 1 to P m dot E is equal to dm system by dt. Typically, mass flow rate is easier to measure than other flow properties such as velocity. When instead of mass flow rate, we may measure velocity of the flow along with the density of the fluid, the mathematical analysis involves integral expressions. There are two systems for conservation of mass, that is open system and the closed system. Let us discuss them now. Conservation of mass for an open system. Consider a section of pipe used in transporting a fluid. For a control volume shown for this open system, a fluid with a velocity u is entering the system across a differential area dA. Velocity, a vector quantity, possesses both a magnitude and direction. As seen in the figure 1.2, only the component of velocity vector normal to the area dA will cross the system boundary. The other component u subscript tan, the tangential to the area, has no influence on our derivation. Thus, if the fluid particle crossing the boundary has a velocity u subscript n, then the rate of mass flow into the system may be expressed as dm dot is equal to rho into u subscript n into dA. Integrating over a finite area, m dot is equal to integral a rho into u subscript n into dA. The previous equation for mass flow rate will apply for inlet and exit cases. The total mass of the system may be expressed as a product of its volume and density. That is, m is equal to integral over volume V rho into dV. Substituting this quantity in the law of conservation of mass equation, integral A inlet rho u into dA minus integral over A exit rho u dA is equal to d by dt integral over volume V rho dV, as shown in equation 1.9. The previous equation is somewhat complicated because of the integral and differential operators. However, this expression may be simplified for two common situations encountered in engineering systems. First, if the flow is uniform, then all the measurable properties of the fluid are uniform throughout the cross-sectional area. These properties may vary from one cross-sectional area to another, but at the same cross-section, they are the same in this radial direction. For example, fruit juice flowing in a pipe has the same value of its properties at the center and the inside surface of the pipe. These properties may be density, pressure or temperature. For a uniform flow, we replace the integral signs with simple summations and we get as shown in equation 1.10, that is sigma inlet rho un dA minus sigma outlet rho un dA is equal to d by dt of integral volume V rho dV. The second assumption we will make is that of steady state, that is, the flow rate does not change with time, although it may be different from one location to another. If there is no change with time, then the right hand term must drop out. Thus, we have equation 1.11. Sigma inlet rho un dA is equal to sigma outlet rho un dA. Furthermore, if we are dealing with incompressible fluid, a good assumption for most liquids, that is, there is no change in the density. Thus, the equation 1.11 further simplifies to equation 1.12, where sigma inlet un dA is equal to sigma outlet un dA. the product of velocity and area in volumetric flow rate. According to conservation of mass principle, for a steady, uniform and incompressible flow, the volumetric flow remains unchanged. For compressible fluids such as steam and gases, the inlet mass flow rate will be the same as the exit mass flow rate. Let's move to conservation of mass for a closed system. We have learnt that in a closed system, mass cannot cross system boundaries. Therefore, there is no time rate of change of mass in the system. Or else, as shown in equation 1.13, dm system by dt will be equal to 0. That is, the system flow is equal to constant. Section 5.3, Material balances. Material balances are useful in evaluating individual pieces of equipment such as a pump or a homogenizer, as well as overall plant operations consisting of several processing units. For example, a tomato paste manufacturing. Composition of raw materials, product streams and byproduct streams can be evaluated by using material balances. The following steps should be useful in conducting a material balance in an organized manner. Step 1. Collect all known data on mass and composition of all inlet and exit streams from the statement of the problem. Step 2. Draw a block diagram indicating the process with the inlet and exit streams properly identified. Draw the system boundary. Step 3. Write all the available data on the block diagram. Step 4. Select a suitable basis such as mass or time for calculations. The selection of basis depends on the convenience of computations. Step 5. Using equation 1.5, write material balances in terms of selected basis for calculating unknowns. For each unknown, an independent material balance is required. Step 6. Solve material balances to determine the unknowns. Conservation of energy. Conservation of energy and energy balances are based on laws of thermodynamics. First law of thermodynamics. Energy can be neither created nor destroyed, but can be transformed from one form to another. Second law. No process is possible whose sole result is the abstraction of heat from a single reservoir and the performance of an equivalent amount of work. These concepts are dealt in detail in an exclusive thermodynamics course and not under the purview of the present module. Energy balance is based on the first law of thermodynamics and is depicted as follows. Total energy entering the system minus total energy exiting the system should be equal to change in total energy of the system. Therefore, when a system is undergoing any process, the energy entering the system minus that leaving the system must equal any change in the energy of the system. In terms of formula, E in minus E out should be equal to delta E of the system. We can also write the energy balance per unit time as a rate expression. E dot in minus E dot out should be equal to delta E dot system. Heat transfer between a system and its surroundings is probably the most prevalent form of energy that we observe in many food engineering systems. Heat plays a major role in cooking, preservation and creating a new food products with unique properties. We will denote heat with the symbol Q, and it has got units joule. If heat transfer is from a system to its surroundings, the Q is negative. On the other hand, if the heat is transferring into a system from its surroundings, such as in heating of a potato, the heat transfer Q is positive. If we consider heat transfer per unit time, then we express it as heat transfer rate or rate of heat transfer denoted by small q, and it has got units J by S, that is joule per second or watts. Thermal energy capital Q can be determined, the heat capacity C is known. Thus, Q is equal to M integral T1 to T2 C dt. If the path for energy transfer is under constant pressure, then Q is equal to M into integral T1 to T2 Cp dt, where Cp is the specific heat capacity at constant pressure. The units of specific heat capacity is joule per kg into Kelvin. Under constant volume, Q would be M integral T1 to T2 Cv dt, where Cv is the specific heat capacity at constant volume. The numerical values of Cp and Cv are similar for solids and liquids. However, they may be considerably different for gases. Work encompasses all interactions between a system and its surroundings that are not a result of temperature difference. Example, shaft transmitting energy from a motor to another piece of equipment that is enclosed in the system boundary. The symbol used for work is W and its units are joules. The sign convention used for work is that any time work is done by a system, W is positive. When work is done on a system, W is negative. This is opposite to that of heat transfer. As shown in figure 1.3, consider a case where a small object moves a distance ds due to the application of force capital F. The work done on the system may then be calculated as the product of force and distance, or dW is equal to minus F into ds. The negative sign reflects the sign convention stated earlier. We can calculate the total work done in moving the object from location 1 to 2 as W1 to 2 is equal to minus integral 1 to 2 F ds, which is equal to F into S1 minus S2. The work interaction between the system and its surroundings can be attributed to several mechanisms such as a moving boundary, a gravitational force, acceleration and shaft rotation.